Hi everyone, welcome back to Info 3370, studying social inequality with data science. We recently covered non-parametric causal estimation, where we take subgroups of the population defined by the confounders, look at differences in outcomes across the measured treatment values, and then aggregate across those subgroups to make a population-level average causal effect claim. Today we'll move on to discuss estimation with a model, focusing on ordinary least squares as an example case. Today, our goal is to learn how to estimate causal effects parametrically using OLS. Our data, as before, come from the PSID prediction challenge, which we used previously in class when talking about prediction. As I discussed in the last class, we're going to assume this causal directed acyclic graph in which education's effect on log income can be identified by statistical adjustment for race, parent education, and parent income. Look back at our class on causal assumptions to see how DAGs work and why we might or might not believe this DAG. Model-based adjustment proceeds in a few steps. So first, you're going to fit a model to predict the outcome as a function of the treatment variable and all the confounders. That model says, what's the expected value of log income given an observed value for the treatment and the confounders? You can see how the model is very similar to subgroup analysis in that you could use the model to say what's the expected income across different values of education, conditional on a given observed value of the existing confounders. That's how we're going to use the models today. Once we fit the model, we're going to create two new data frames. One where we set education to the value college, one where we set education to the value high school. Then we predict the potential outcome under each of those treatments for every person in the data set at their observed values of the confounders. Take the difference in those predictions, and that's an estimate of the conditional average causal effect at the confounder values for each person in the sample. And finally, we can make population average claims by averaging over all people, or we can make subgroup average claims by averaging over any subset of the population that might be interesting to us. So let's go ahead and see how this works in R. Here's the course webpage for today, which gives some sample code. And so I'm going to go ahead and begin in my R console, where I've already copied the code over to load the data. So you'll recall that these data contain lots of possible confounding values. We're going to fit a model where, as in our DAG, we're looking at the respondents' log income. They're coded G3 because in this data set we have data on grandparents, parents, and children are G3. We're going to include the treatment variable in the model, the respondent's education. Then we're going to interact that variable with a series of possible confounders: parents' education, parents' log income, and race. Now, we could specify this model any way we want. We could have just used plus signs everywhere here, thus assuming that the effect of education would be the same in every confounder subgroup. Here we've decided to interact the treatment with all the confounders, thus assuming that the confounders do not interact with each other, but the treatment effect might differ across confounders in a way that's perhaps well summarized by a linear additive function of those confounders. That's a conceptual choice. I'm not really wedded to that choice myself, but I think it's often a good one to assume that the treatment effect varies, but the confounding has this somewhat simple linear additive structure. So let's go ahead and fit that model. And if we look at the model, you'll see that it just has a ton of coefficients here because we included all these interactions. The reason for the interactions, of course, is that we think the causal effect varies across population subgroups. Okay, so in this step, we fit a prediction function. Our next step here is going to be create counterfactual data frames to predict. And I can copy this from the website over here. We're going to create a data frame D college, where we intervene to change the value of respondents' education to college, and another one where we change that value to high school. So these two data frames have one row per person. They only differ in that we've changed the value of the treatment variable. So the next step is to predict potential outcomes. So here I'm going to create a new object I'm calling conditional average causal effect. That starts with our original data set and adds a few new variables. So the first, y hat college, is the predicted value of the outcome according to our fitted model object, where the new data is that data set that's exactly the same as the original one, but with the treatment variable taking the value college. Then I'm going to make another prediction for the outcome the respondent would realize if they had exactly a high school degree, where I predict in the data set where we've changed the value of respondent's education to high school. Then finally, I'm defining effect of college as the difference between the predicted outcome under the college intervention and the predicted outcome under the high school intervention. Then I'm just selecting the variables we're using so that this printout is a little easier to read. And I'm going to make my window wider so that we can see those outcomes more easily. Okay, so for the respondent whose ID is 1, we see that the effective college estimate is 0.498. For the respondent whose ID is 4, the estimate is 0.182. So we have this for all these 1365 rows, 1 per respondent, for the predicted average causal effect of college among people who hypothetically look exactly identical to that respondent. We might then summarize the causal effect by making a claim for the population as a whole or for subgroups. So summarize the population average causal effect. So we might take that conditional average causal effect and then summarize and say population average effect equals the mean of each person's estimated effect of college. And this is conditional average effect, not conditional average causal effect. So here we estimate the population average causal effect is 0.258. So similarly, we can do this within population subgroups, such as those defined by parents' education. So here I'm taking that conditional average effect, grouping by the subgroups, and reporting the mean effect of college. And similar to the other day, we're seeing that the effect of college among those whose parents did not finish high school is very large, whereas the effect of college among those whose parents finished college is much smaller. Because after all, these folks have lots of other advantages that support their own income attainment, so that they might realize a high income regardless of whether they go to college or not. Generally, you could estimate, I should label this, summarize subgroup average effects. When estimating subgroup average effects, you could estimate over any subgroups that you want. So we had to adjust for all the confounding variables in our DAG, but we could choose then to report results for any subgroup of interest. So you could look at effects by race, effects by parents' education, effects by parents' income, any of the variables that went into the model. And this is one of the powerful things about adjustment, in this case parametric adjustment, is that we first make our causal assumptions to decide what variables go into the model. That happens in our DAG. Then we make our statistical assumptions. That happens when we fit our prediction function and decide what statistical patterns we're going to learn from the data in what form. Then we create our counterfactual data frames and predict our potential outcomes. Having done this, we're in a great position because we have this data frame where we have a predicted causal effect at the confounder values of every person. That allows us to make population average claims and to look at population heterogeneity across subgroups very easily. So this is a reason why parametric adjustment carried out in this framework is really helpful, because we predict the causal effect at the confounder values of each person. So our learning goals for today were to estimate causal effects parametrically with OLS. Now you've got in your belt the toolkit of non-parametric estimation and also parametric estimation with OLS. These also lay the groundwork for other kinds of estimation, like estimation where you predict potential outcomes with machine learning estimators, because as you can see, what you really need is to make your causal assumptions fit a predictive model, then predict the potential outcomes for all the people in the sample.